In this next lesson, we're going to look at diagrams or pictures that are called Lewis dot diagrams. A Lewis dot diagram shows an element symbol surrounded by dots that represent valence electrons. Remember that valence electrons are the ones in the outermost energy level. To draw a Lewis dot diagram, the first thing you need is the element symbol, and this represents the nucleus and the inner electrons. The inner electrons are not part of the bonds, which is what Lewis dot diagrams are used for, so we don't need to draw those inner electrons. Then once you have the element symbol, you can begin filling in the valence electrons. One electron to start off with goes into each of the 4 orbitals. The orbitals are just locations where your electrons can be placed. We're going to use the top and bottom and the 2 sides of our element symbols to represent those 4 orbitals. If you have more than 5 electrons in the atom or ion, then you begin pairing up those electrons into those 4 orbitals. So each of those 4 orbitals could contain either 0 electrons, 1, or 2. Let's look at a few examples. First one we're going to look at is the sodium atom. So we want the element symbol, Na, and that represents the nucleus and the inner electrons. To determine the number of valence electrons, go to your periodic table and look at the very top and find the group number. The group number will tell you the number of valence electrons in any atom. So for sodium, group number 1, we can draw the 1 valence electron in any of the 4 orbitals. It doesn't matter which one you put it into. Underneath that, our next example is the oxygen atom. So again, we want the symbol. And then looking at the group number, we figure out the valence electrons. Oxygen is in group 16, so we take the last digit, 6, and that tells us the number of valence electrons. So the first 4 go into our 4 orbitals, top, right, bottom, and left. And our next 2 now, we pair up with the ones that we've already drawn. When you're drawing these, it's best to start in one spot. I usually start at the top, and work in one direction and continue that direction as you're filling in. The next example to the right is the sodium ion. We need to know the charge of the ion to know whether we've lost or gained electrons and how many. Sodium ion has a charge of +1. So again, we want the element symbol Na. The charge of +1 tells us that this ion lost 1 valence electron. So the one that we had in the atom has now disappeared. It's gone somewhere else. So we put square brackets around that symbol and the charge to show, yes, that valence energy level is empty. For the oxygen ion that has a charge of -2, we need to put 2 extra electrons in. The charge of -2 says that this ion has gained 2 electrons. So again, oxygen has symbol O. We would start with the 6 electrons that the atom has. And now the charge of -2 means we've gained 2 more electrons. Square brackets and the charge of -2 on the outside. So this time the octet is full. If you draw the electrons as X's, dots, doesn't really matter. I've just drawn the 2 that we've added as X's so that we can distinguish between what we started with on the atom and the 2 that the ion gained from somewhere else. If we look at a diagram, we can classify the electrons as either bonding electrons or lone pairs. A bonding electron is an unpaired electron and it's trying to bond with something. Electrons are satisfied or most stable when they are paired up, so they're looking for something else to pair up with. A lone pair, a paired set of electrons, has already found their pair, so we don't want to do anything with them. We want to leave them alone. If we look at a nitrogen atom that has 5 valence electrons, we can label our lone pairs and bonding electrons. So at the top of this diagram, I have a lone pair. These won't be part of our bonds to other atoms in our molecules. So lone pairs, leave them alone. The 3 electrons that are unpaired are bonding electrons. So these are the ones that are going to be looking for something else to pair up with so that there are 2 in those orbitals. Ionic compounds are the result of an electrostatic attraction of a positive and a negative ion. Might be a slightly different definition than what you remember from Science 10. You may have thought of it as a metal with a nonmetal. But if we include those polyatomic ions that are on your periodic table, we need a slightly different definition that's more inclusive. So attraction of positive and negative ions results in an ionic compound. We can use our Lewis dot diagrams of ionic compounds to show each one in square brackets, just like we did before with its charge. Here's 2 examples of ionic compound formulas, and we'll draw Lewis dot diagrams so that we can see how these pair up with each other to form stable compounds. Calcium chloride is a pairing of a calcium 2+ ion and 2 chloride ions, which are each -1. So if we draw each of those out, the calcium ion with the charge of 2+ has lost 2 electrons. Each of the chloride ions has a charge of -1. They've gained an electron. So not just the 7 that it had as an atom, but now 1 more electron that it has gained from somewhere else. And where it's gained from is the calcium. Now, calcium gave away 2 electrons to B2+, so we've got 2 chloride ions, each of those taking one of those electrons from the calcium. Same idea for the aluminum oxide. Aluminum as an ion is Al3+. Oxide is an oxygen with a 2- charge. We have 2 aluminum ions, and each of those ions gave away 3 electrons to have the charge of 3+. Each of the oxygens has gained 2 electrons. So the 6 electrons from the atom and 2 more that it has gained from the aluminum. So we have 3 aluminum ions that each, 2 aluminum ions that each gave away 3 electrons, and 3 oxygen ions that has each gained 2 more electrons. So a total of 6 electrons that were lost by the aluminum were picked up by the oxygens.